Hello everyone, welcome to Cyber Platter. This is a video on ISC Square CCSP to help you prepare for the certification. Today we will cover part 3 of Domain 5, Cloud Security Operations. So this is the agenda for today. We will be discussing how to manage physical and logical infrastructure for cloud environment. We will be talking about access controls for remote access, that is RDP, SSH, baseline compliance monitoring, patch management, hardware monitoring, performance monitoring, network security controls, management plane, etc. The first topic is remote access, right? So if you see how the cloud is set up, all the customers and users require remote access to use and manage their logical environment. And also remember that for physical environmental access, it should be restricted to a very few privileged cloud service provider employees, right? Some of the common remote access methods used are VPN, that is virtual private network, RDP, remote desktop protocol, secure terminal access, and secure shell SSH. Some of the threats that the security professional should consider regarding remote access are lack of physical security controls, unsecured networks, infected endpoints accessing the internal network, external access to internal resources, etc. Now let's see what are the key features of remote access solution, right? The first one is session control. Session control includes access approval, session duration limits, idle timeouts, etc. Next one is log and audit trail. We should have this for all the connections. Audit trail provides accountability. Real-time monitoring of activities and recorded sessions should be there, okay? Isolation between the connecting user's desktop and the host that the user is connecting to, that is virtual desktop infrastructure VDI, it should be there. Isolation is a must. Secure login with complex passwords or certificate based login. Encrypted transmission of all communications between the remote user and the host. And then there should be two-factor authentication providing enhanced security. Also remember that no matter which remote access methods are deployed and used, we must always ensure that the underlying systems supporting remote access are hardened, that is, OS baselines are used, vulnerabilities scanned and patched, monitored for suspicious activity like using event logging and other controls, right? Applying baselines is an important step to ensure consistent and secure operating systems. Once OS baselines are applied, it's important to ensure that systems remain in compliance with those baselines through continuous monitoring. So, monitoring is very much required. Compliance can be accomplished by using configuration management tools with automated baseline scanning functionalities. You load these tools with your approved baselines for each OS and scan your infrastructure to detect any non-compliant systems. Some of the unexpected configurations that you can come across are, say, suppose your baseline was not applied to all the systems either intentionally or accidentally. A legitimate administrator made an unauthorized change to a system, right? A malicious outsider gained access to a system and made modifications. For example, discovering an unauthorized open port may be an indication that a hacker has set up backdoor communication. A system has an approved policy exception that the baseline scanner did not account for. For example, port 80 may be disallowed in your Linux baseline but allowed on a handful of web servers that use HTTP instead of HTTPS. Now let's see what is patch management. Patch management is a subset of configuration management that includes all processes for finding, testing, and applying software patches or code changes to your systems. Patch management includes more than just vulnerability management, although that is a huge part of this. So patches are released by software and firmware vendors, and these are made available to their customers to install. The patches typically provide new functionality, improve stability, or of course fix known vulnerabilities, right? NIST SP 840 Guide to Enterprise Patch Management gives a great overview of patch management. It's a great reference, right? Next, we'll see patch management process. Every organization should develop a patch management policy that identifies which assets require what type of patches on what schedule. Also, the organization should create and maintain a set of patch management procedures that define what steps to take in order to acquire relevant patches, validate their appropriateness for their, environment, apply them to all the assets and test their effectiveness. The first step is to identify that there is a vulnerability and a required patch actually exists for that vulnerability, right? This step entails gathering information from all relevant vendors about all outstanding patches for all your software and firmware. In most cases, vendors offer notification mechanisms or other means for customers to quickly identify when new patches are released. This step can be quite tedious for large public clouds with many systems and numerous types of software. All outstanding patch information should be aggregated into a database or patch management tool for consistent, automated, and streamlined deployment. The next step is acquire. After identifying that patches exist for our environment, the next step is to actually obtain those patches by downloading the appropriate executables, scripts, or packages. Some software can directly connect to the vendor website and download relevant patches directly within the software itself, while other software requires navigating to the vendor's website or other means and then download it, right? Your patch management procedure should include documented steps to procure patches for each vendor within your environment. The next step is test. Many vendors provide hashes to validate the integrity of their patches after downloading. This prevents compromised patches being applied to our systems. But regardless of whether you have a hash or no, you should first test patches in a development environment to ensure that they don't break your systems or introduce new risks. Once you confirm that a patch causes no harm, then you can approve it for deployment or installation. So the next step is deploy. So remember that all of this process should be included in configuration management process. There should be a plan for this, no? There should also be risk management in case of unexpected outcomes after applying patches, right? That is a rollback plan, how it should be done. Okay. Once we have acquired and tested our patches, we can go ahead and deploy them across the production environment. But before this, make sure to notify the customers if it is required, like, if there is a downtime or anything, or it is included in your contract. And then we should consult our patch management policy to determine the appropriate patching schedule. In many cases, organizations implement deployment windows during which patches and system updates can be made. Automation is very critical here, right? Because especially in a cloud environment which is so huge, in most cases, cloud infrastructures rely on patching baseline images and redeploying those baselines to impacted systems. Patching images removes the need to individually patch thousands of systems and reduces the risk of one-off errors. So the next step is validate. This is the final step where we validate that the patches are installed properly and confirm that everything is in working order. In some cases, it can be as simple as looking for confirmation messages, but others can be as involved as running tests to ensure the underlying host is operating as expected. So to summarize, a patch management process should address vulnerability detection and evaluation by the vendor, subscription mechanism to vendor patch notifications, severity assessment of the patch by the receiving enterprise using that software, applicability assessment of the patch on target systems, opening of tracking records in case of patch applicability, customer notification for applicable patches if required. There should be change management process, successful patch application verification should be there, issue and risk management in case of unexpected troubles or conflicting actions, closure of tracking records with all auditability artifacts. There should be a rollback plan as well. And all of this should be properly documented and updated, right? The next topic is patch management implementation. Patches can be applied with mechanized tools or by personnel. There are obvious benefits and risks for both the methods. The operator will have to decide what is the best, right? Is it automation or is it manual? So first let's see about manual patching. Trained and experienced personnel may be more trustworthy than a mechanized tool and might understand when there is an unexpected activity, right? However, with the vast number of elements that will need to be patched in a cloud data center, the repetitiveness and boredom of the patch process may lead even a seasoned administrator to miss a number of targets. Moreover, the process will be much slower than the automated option and may not be as thorough. Next one is automation, that is automated patching. A mechanized approach will allow for much faster delivery to far more targets than a manual approach. Patch tools, right? They might also include a reporting function that tells us which targets have received the patch, cross referenced against the asset inventory, and have an alerting function to inform the administrators which targets have been missed. Without a capable human observer, however, the tool might not function thoroughly or properly. The patches might be misapplied, or the reports might be inaccurate or portray an inaccurate picture of completeness. So, now let's see the challenges of patch management. Lack of standardization, right? There's a lack of service standardization for enterprises transition to the cloud. Lack of standardization is the main issue. For example, a patch management solution tailored to one customer often cannot be used or easily adopted by another customer. The next one is collaboration. Patch management is not simply using a patch tool to apply patches to endpoint systems, but rather a collaboration of multiple management tools and teams, such as change management and patch advisory tools, right? And to get all the teams to work at the same time might also be very difficult. Complexity in a large enterprise environment, right? Patch tools needs to be able to interact with a number of managed entities in a scalable way and handle the heterogeneity that is unavoidable in such environments. To avoid problems associated with automatically applying patches to endpoints, thorough testing of patches beforehand is absolutely mandatory. The next challenge is multiple time zones. As the patch is pushed throughout the environment, the actual date or timestamp may become an important and misleading matter in acquiring and acknowledging receipt. For example, say that an automated tool requires an agent that is installed locally on each target. If certain targets are not running when the patch happens and won't be operating until the next calendar date, then the local agent may not receive the patch because it may check against the central controller for patches for that current day, right? And this problem increases when patch agents are set to check for patches according to a time specified by the internal clock, and different targets have internal clocks set to different time zones. Also, remember that this problem is not limited to only automated tools. If a manual method is used, the administrators may be applying a patch at a given time or date when not all customers and users have their targets operating. So, those targets might not receive the patch only, right? And the administrators might not realize that targets that don't currently appear in scans may need to be patched at some later time or date. Moreover, if patches are being applied manually, the process will necessarily be extended so that the administrators can be sure to reach all potential targets as they come online. And also, right, VMs that are physically located in the same time zone can be configured to operate in different time zones. For some patches, the correct behavior is to apply the patches at the same local time of each VM. For the others, the correct behavior is to apply at the same absolute time to avoid a mixed mode problem where multiple versions of software are concurrently running. This might also result in data corruption, right? So some of the questions that appears under multiple time zone challenges are that how can a patch be applied to thousands of VMs at the same time across multiple time zones? How do we coordinate maintenance mode windows for such a deployment activity? Is the change management function aware of the need to patch across multiple time zones? If it is, has a rolling window has stipulated and approved for the application of the patches. So multiple time zones itself is a huge topic, right? So the next one is VM suspension and snapshot problems. So all this that we discussed, all these possibilities that we discussed in multiple time zones, right? They are all escalated in a cloud arrangement because of the wide use of virtualization. All virtualized instances saved as images and not currently instantiated during the patch delivery will be receiving the patch only after they are next booted. This means that the process will endure until all virtual machines have been made live, which could represent a significant amount of time after the decision to implement the patch, right? The result is a relatively long delay between the time the operator decides to implement the patch and the time of 100% completion. This reflects poorly on the process and the operator, especially in the eyes of regulators and courts. So, the optimum technique is to combine the benefits of both manual and automated approaches. Manual oversight is valuable in determining applicability of patches and testing patches for suitability in the environment, while automated tools can be used to propagate patches and ensure uniform application. Regardless of the approach taken, patching should be mentioned in the SLA, and an agreed upon schedule and threshold of patches is an important contractual consideration. Also, right, one more thing that I wanted to mention regarding patching is that in some cases, organization may give blanket approval for applying patches which addresses imminent risks, allowing these patches to bypass standard change management process. Change management will take place after the fact. Okay. So now let's see about performance and capacity monitoring. Performance monitoring is essential for the secure and reliable operation of a cloud environment, right? Data on the performance of the underlying components may provide early indications of hardware failure. And also, unmonitored capacity could allow for total consumption of resources, which can lead to resource starvation and a serious impact on performance. Let's see what needs to be monitored in this area. There are four key subsystems, right? First one is networking. Here we monitor for excessive dropped packets. The next one is compute, excessive CPU utilization. The next one is disk. Full disk or slow reads and writes to the disks are monitored here. That is input output operations per second, IOPS. The next one is memory. Excessive memory usage or full utilization of available memory allocation is monitored. About these four, right? Four pillars, that is network, compute, disk, and memory. We should know about vendor specific monitoring recommendations, best practice guidelines, and thresholds for performance, right? And also remember that in a shared environment, monitoring is crucial for maintaining an acceptable level of performance. So, for 24/7 monitoring of the cloud environment, we require adequate staffing. One option is to outsource the monitoring options to a trusted third party. But remember, you have to have due care and due diligence in place if you're pursuing outsourcing option, right? So there should be a potential vetting process when you're considering a cloud monitoring partner, and you should have things like having HR check references, examining the terms of any SLA or contract being used to govern service terms, also executing some form of trial of the managed service in question before implementing into production. The next topic is hardware monitoring. Though whenever we think about cloud environments, the first thing that comes to our mind is virtualized infrastructure. But there is always physical infrastructure underlying it, and this has to be managed, monitored, and maintained. Some of the items that needs to be monitored here are environmental temperatures, temperature within the hardware, fan speeds, failed drives or drive errors, hardware components like CPU, memory, cards, etc., network devices, and here we are not just considering the servers, right? Everything else. The next topic is backup technology. Configuration data for hosts in the cloud environment should be part of the backup plan. You should conduct routine tests and restore hosts as part of the disaster recovery plan to validate proper functioning of the backup system. Okay. We need to understand what the critical configuration information is for all the infrastructure that we manage and ensure that this information is being backed up consistently in line with the organization's existing backup policies. Also, ensure that this information is being integrated into and accounted for within the business continuity and disaster recovery plan, that is BCDR plan of the enterprise. Now let's see some of the backup technology types. First one is snapshots. A snapshot is a copy of a virtual machine, its virtual disk, and any settings and configurations associated with the VM. The snapshot is saved to disk as a simple file. Snapshots are often performed before deploying software patches or other potentially unsafe operations in a virtual machine. Okay. If something should fail, snapshots are a great way to roll back to a specific point in time. Snapshots should be differentiated from backups for a couple of reasons. Snapshots are not complete on their own and rely on the virtual machine's parent disk and file system. If the parent disk is deleted or corrupted, a snapshot cannot help you restore your system, right? Snapshots are saved on the same storage infrastructure as the VM itself. With true backups, it's important to keep the backup completely separate from the original data. VM snapshots are neither separate from the underlying physical host nor the virtual infrastructure of the VM. Okay. The next one is agent-based backups. Agent-based backup mechanisms were considered the gold standard when virtualization first became popular. Agent-based backup requires installing a component, the agent, on every system in your environment that handles the backup duties and sends it over to your desired backup storage. Being installed directly on a system gives agent-based backups an edge when particular systems or applications require direct access to perform complete backups. The downside is that agent-based backups can become hard to manage in large environments, just for example, public cloud. The next one is agentless backups. Agent-based backups doesn't mean that there are no agents, but instead require a single agent be installed on a given network, right? This single agent provides centralized network-wide backup capabilities without you needing to somehow interact with every endpoint. Generally speaking, the more systems you have to back up, the more attractive agentless solution becomes. So for a cloud environment, agentless backup tends to offer great control, simplified management, and lower cost than agent-based solutions. Agentless backup requires a fully virtualized environment. So networks with both physical and virtualized servers require an agent-based or hybrid approach. And also agentless backup doesn't work with every system. And so it is important that you consider your architecture before choosing any backup solution. Backup and restore challenges. The biggest challenge with backup and recovery is understanding the extent to which you have access to the host and what configurations can be changed. Control. In the cloud, we make changes through a management interface, but we don't see what is actually happening in the background. We must be confident that the changes we make are the only changes that are occurring. Next one is visibility. The ability to monitor the status of a consumer's data and programs and how consumer data and programs are being accessed by others. Next, we will see about network security controls. In addition to securing the hardware and logical configurations, right, the provider will have to ensure that the networking architecture and components are secure too. This will often involve many of the same tactics and methods that we use in the traditional environment, as well as some cloud-specific permutations. The first one is firewalls. Firewalls are tools that limit communications based on some criteria. They can be either hardware or software or a combination of both. Firewalls can be standalone devices or integrated into other network nodes such as hosts and servers. The criteria for determining which traffic is allowed and which is not can take the form of rules, such as which services or protocols are allowed, which ports can be allowed, from whom and when traffic should be allowed, and so on. The criteria for determining which traffic is allowed can also be based on behavior sensing algorithms. That is, the firewall is taught which behavior is normal for both environment and the user, and deviations from the normal baseline are noted by the firewall. And there is stateful inspection as well. The firewall understands the expected pattern of conversation in a protocol and recognize deviations. There is also inspection of content. There's also host-based firewalls and network-based firewalls, right? The next one is IDS IPS, intrusion detection systems and intrusion prevention systems. These are very similar to firewalls in that they monitor network traffic. Just like how we talked about firewalls, right? These can also use defined rule sets, behavior based algorithms, content, or stateful inspection to detect unexpected activity. The explicit difference between an IDS and an IPS is that an IDS only reports suspicious activity, whereas the IPS can be set to take defensive action when suspicious activity is recognized. For example, closing ports and services. Even in this, we have network IDS, network IPS, host IDS, host IPS, right? Honeypots. A honeypot is a tool used to detect, identify, isolate, and analyze attacks by distracting attackers. This is usually a dummy machine with useless data partially secured and configured as if it was a realistic portion of the production environment. The security team can monitor and record the attacker's behavior when the attacker penetrates a honeypot and attempts malicious activities such as installing rootkits or other malware, escalating their privileges, or disabling functionality. This information can be used for defensive purposes in the actual production environment or as evidence in litigation and prosecution actions. The next one is vulnerability assessments. A vulnerability assessment is a scan of the network in order to detect known vulnerabilities. These can be automated so that they are scalable for networks of any appreciable size. The unfortunate flaw in vulnerability assessments is that they only detect known vulnerabilities. Any vulnerabilities that are not part of the scan will go unnoticed. Vulnerability assessments can't prevent attackers from discovering previously unknown vulnerabilities in systems and attacking them. These forms of attacks are often referred to as zero-day exploits. Network security groups. Most cloud providers use the notion of a security group, which is basically a network ACL that operates at the VM level rather than the network level. In many cases, security groups may not be fully featured as network ACLs, but the core functionality is the same. A network security group, however, is a feature popularized by Microsoft that effectively combines the concept of security groups with network ACLs. Network security groups allow you to control traffic to and from either an OS or an entire network. Virtual Machine Introspection (VMI). This allows for agentless retrieval of the guest OS state, such as the list of running processes, active network connections, and opening files. VMI can be used to perform external monitoring of the VM by security applications such as an IDS or an IPS. This monitoring is widely used for malware analysis, memory forensics, and process monitoring. The next topic is management plane. Managing the physical and logical infrastructure of a cloud environment requires effective task and operation scheduling, effective orchestration of activities and resources, and comprehensive yet minimal disruptive maintenance. All of these activities take place in the management plane. So the management plane, right, provides access to manage hardware, and that is through baseline configurations, logical infrastructure, that is task scheduling, resource allocation, software updates, networking, that is network management, routes, access lists, security groups, virtual switches, VLANs. The management plane is high risk and must be protected with access control, logging, isolated network, etc. So now let's, like we discussed in the previous slide, scheduling, orchestration and maintenance. Let's see those in detail here. The first one is scheduling. Cloud infrastructures involve managing a large variety of virtualized resources, and cloud providers employ task scheduling to fulfill and manage customer requests related to those resources. Scheduling and resource allocation go hand in hand. Scheduling is the process of taking customer resource requests and prioritizing those requests in such a way that available resources are assigned and utilized most efficiently. When multiple customers request compute power, for example, the cloud provider's task scheduler considers the nature of each request, whether it is for CPU or GPU, etc. Right? The size of the request, that is how much compute power is needed, the length of time the resource is needed, and the availability of suitable resources. Based on all these factors and other metrics, the schedulers' algorithms determine which customers to supply with the appropriate resources at what time and for how long. Proper scheduling enables efficient resource utilization and keeps request pipelines moving smoothly. The concept of distributed resource scheduling, DRS, comes into play here, okay? The next one is orchestration. Orchestration is the organization and integration of automated tasks between systems and services in a cloud environment. Cloud orchestration allows you to create a consolidated workflow for multiple interconnected processes. With orchestration, you can automate complex processes such as resource provisioning, allocation, and scaling. Orchestration is absolutely required to enable cloud providers to provide high availability, dynamically scaling services to customers with little to no human interaction. Remember that automation refers to a single task or process. Orchestration is the coordination and management of these automated tasks into a streamlined automated workflow. The next one is maintenance. One of the critical components of managing a cloud environment is conducting routine and emergency maintenance of the physical and logical infrastructure. In traditional data center environments, right, operators serve very few customers, maybe even a single customer, which may be themselves. This type of independence lets data center operations team easily find the best time to conduct maintenance simply by coordinating with their users. Public cloud infrastructures that serve thousands of customers simply don't have this luxury. Cloud providers need to carefully consider potential customer impact when invoking maintenance mode, and they should ideally leverage orchestration tools to minimize and even remove this impact altogether. Whenever possible, customer workload should be automatically routed to stable systems while maintenance occurs on physical or logical resources. Anytime a cloud service provider suspects that maintenance might impact customers' performance or availability, the provider should communicate this to all potentially impacted customers as soon as possible with details of the maintenance window and its expected impact. So this brings us to the end of part 3 of domain 5. I will see you in the next video. Until then, take care of yourselves. Bye bye.